All right, today's lesson is on osmosis and tonicity, Tonicity, which is said like tonicity. Last week, we talked about diffusion. So as you can see, the molecules in the cup are diffusing from an area of high concentration to an area of low concentration until it reaches equilibrium. And eventually, if we sit here long enough, we would see that it would indeed reach equilibrium. Now, what you can't see, my view of it, is that it's not absorbing in. You can see that there's a whole lot of clear there. And so I'm going to set that aside, and by the end of this lesson, it should be completely diffused. Today we're going to put together the cell membrane, which you should understand and what it's made of and how it works. And we're also going to add in what happens when you're in a situation where you're not in equilibrium, when everything is not equal inside and outside the cell membrane and what happens. But first of all, you need to understand two terms. I'm going to put our little visual aid back. So we have a solute and we have solvent. Okay. So solute in this instance was my red food coloring. Okay. Solute was what is being dissolved or diffusing into the water, and the solvent is water. Now, water is a very common solvent. In fact, it's called like the universal solvent because it can dissolve anything. So solvent is the liquid that is doing the dissolving. It's the great dissolver, while solute is what is being dissolved. So if you're making lemonade, this is your water, the solvent is your water, and the solute is like your lemonade powder, since I'm sure you make it with lemonade powder like I do and not with squeezing lemons. If you make it by squeezing lemons, then the lemons are your solute, okay? But we need to know those things because everything we're going to talk about today depends on if you know what solvent and solute mean. Together, solute plus solvent equals solution. And so we are going to be dealing with solutions all video long, okay? I guess it only equals one solution, okay? So what we need to know is if we have a situation where things are not equal on both sides of the cell membrane. So say you have a little membrane here, and of course, it's not a cell, it's a cup, but whatever. So say you have a little membrane here, and it's full of water. Okay. And then you put in some sugar, and on this side, and the sugar can't cross the membrane. So these little dots here are sugar molecules. Okay, so this is a semi-permeable membrane, so it's only able to let some things out, like the cell membrane is. Can't even read that. So it's a semi-permeable membrane. Sugar cannot cross, water can. What's going to happen here? Well, first of all, what is the solute and what is the solvent? So what is the solute? The solute is sugar, that's right. So that's the solute. And the solvent is the water. Okay, so the water is going to be what has dissolved the solute to make a solution, but it's not equal. So what we're going to see here is we are going to see water move to where there's higher solute concentrations, okay? So on this side, it's high solute. Okay, and on this side, it's low solute. Can you see that? Can you see how there's low solute on the left or on this side of it, and there's high solute on the right, okay? Water is going to move to the high solute side, and you can think of it as like there's so much solute over there that it needs to like dissolve it, so it needs more water. But what it's really doing is it's trying to reach equilibrium, and it's doing it kind of like, well, it does it naturally, so it's not like doing math or anything, but it's kind of by a percentage. So if you have like 10% sucrose or 10% sugar on the high solute side, and you have like 2% on the low solute side, well, we need to balance that. We need to balance it and try to get like, I don't know, 5% on both sides or whatever it would be, 5.5 or 6% on both sides. So the sugar can't move to make that balance happen. The sugar is unable to pass through the semi-permeable membrane. It can't move to make that balance happen. Instead, the water has to do the work. So the water is going to go to the right, and then it'll set the balance so that then, of course, even though there's still more sugar on the right side, there's also more water, which will bring that percentage of sugar down, which is kind of what it needs. Okay. So there's 3 types of solutions that you have to know, or 3 types of situations, because it doesn't have to be a solution. I'm going to pretend like we have a nice little beaker of liquid here, and inside of it, we've dropped a cell. All right, so obviously highly magnified, okay? So we've dropped a cell in there, and the cell has 12% solute. Okay, the beaker has 25% solute. First of all, if it's got 12% solute, how much water does it have? Well, it's just a solution that only has solute and solvent. So if it has 12% solute, all the rest is water. Okay, so that's going to be 88% water. So what about this one? How much water's out here? 75% water. I'm writing H2O to shorten it, okay? And I squished it and made it ugly because that's how I roll. Okay, what's going to happen in this situation? Okay, the membrane's not permeable to the solute. So the solvent, the water has to move. Well, it looks to me like there's 88% water here, and there's 75% water there. So it looks to me like water is going to go that way, moving towards the high solute. That's what water does. Why? Because there's an imbalance. There's an imbalance, and we need equilibrium. We want equilibrium as the goal. Okay, so equilibrium is the goal. That's what the cell will do naturally. It will try to reach equilibrium. Now, sometimes you might have heard a word called homeostasis. Okay, homeostasis is a big word that basically means keeping a balance. Okay, keeping a balance in the cell. The cell has to have a balance. If it doesn't have a balance, then you're going to end up with bad things happening, like not enough water to do your work, or too much of a toxin. And so that's why, first and foremost, things move by passive transport. If there's too much, some leaves. It goes through the little membranes. If it has to be pumped out, it will. But overall, cells need homeostasis, which is regulation of just keeping of a balance in the cell. And it's homeostasis for salt, for water, for all kinds of things, okay? So in that situation, here comes the vocab. Get your notes ready. In that situation, where we had a cell that had higher solute on the outside, low water, compared to the cell. So it was the cell itself was dropped into a solution, and the solution then comparatively, right? Because I mean, it depends on where you drop it into. Maybe this would be a high solute in some other solution. So these are comparative terms, like I'm short. Okay, maybe not in a classroom full of kindergartners, but in a classroom full of high schoolers, I'm short. So that's like a comparison term, right? It's subjective, okay? Same thing here. So high solute, yes, in this situation, it was a high solute, but it's just because we're comparing it to the cell. And so what's going to happen here? Well, the water's going to leave to go out, right? So this is called a oh, good grief. I just keep going back and forth and running out of space here. So this is called a hypertonic solution. Okay? Because it's hyper, because hyper means high. So maybe it's like high energy, right? Hyper energetic. You maybe heard of a hyper person that's high energy. So hypertonic means it's high, and tonic refers to the solute. High dissolved stuff in it. Well, that's a nice definition. So now hypertonic, I have to say what I'm referring to. So I have to say a hypertonic solution. So the solution the cell is in is hypertonic. Hyper means high, and tonic is solute. So high solute. And then the solution is what we're talking about, what you drop the cell into. Okay? So that means that, well, the cell isn't hypertonic. No, it's the opposite. The cell is hypotonic. So it's a hypotonic cell. Hypo means under or low. And tonic, of course, means solute. Okay, so maybe you've heard of a hypodermic needle, kind of a gross little thing, but a hypodermic needle would just go like right under your skin, dermis being your skin. So hypo would be under the dermis. So hypo means under or low, and tonic is the solute. And so the cell in this case is the low solute. So it's the hypotonic part. If there's a hypertonic, then there's a hypotonic, and you just have to say which is which. Okay, hypertonic is the high solute. The water's always going to move to the hypertonic part, okay? Because it's going to move where there's a high solute, right? Because if there's a high solute, then there's a low water, because there's only two parts, solute and water. If there's high solute, there's low water. So the water's got to move that direction. So the water always moves towards the hypertonic. Write it down. The water always moves toward the hypertonic, okay? And so that's basically what you have to know about that. Meanwhile, our cute little cup is completely diffused. Isn't that cute? Okay. Now I could say, hey, is this a hypertonic solution or hypotonic? You know what? It's not one, because there's only the solution. There's nothing in it. But if I were to put something in it, say I put in it a bag of sugar water. If I were to put a bag of sugar water in it, like some of that sugar water we used in our lab last week, if I were to put a bag of sugar water in it, then the sugar water bag would be high solute, because there's no sugar in that water. So that would be the low solute. So what would happen? The water would move into the bag, because it always moves towards the high solute or the hypertonic area. Now, what if by some amazing coincidence you had a 10% solute here? Now, I say solute, I don't say sugar or anything like that, because it could be anything dissolved in it. It could be 10% salt, it could be 10% sugar, it could be 10% iodine, it could be whatever. It's just something dissolved. That's why we use the term solute, because it could be anything. What if I have like that? Equal. Oh, that's another word. Isotonic. Yeah, iso means equal. Equal solute. What's going to happen now? I bet I just tricked you. Water is not going to just stop. Water is going to move into and out of the cell equally, but we call that no net movement. Why? What does net mean? It means like it's not moving one direction or the other more. Okay, it's moving in and out equally. There's still movement. So I'm not saying no movement. I'm just saying no net movement. Like it's not moving greater to one area or another. It's like equal movement. Okay, let's do 1 or 2 practice problems really quick, and then we're done. Okay, so if I have a situation where I have a little black marker's not working very good. I have a little cup, and my little cup, I drop a cell into it. Okay. And it's, let's say the cell is 21% solute, and the solution is 17% solute. What's going to happen? Is the cell going to get larger or smaller? Okay. I don't know what you said because I can't hear you. But what I know is that water always moves to the higher solute. So in it goes. So the cell's going to get larger. Okay. Is the cell, when you first dropped it in, was the cell hypertonic, hypotonic, or isotonic to the solution? I still can't hear you. It's hypertonic. That's right. Hypertonic cell, hypotonic solution. Cell will get bigger. Okay, you could do some practice problems too. In fact, you're going to do a whole little practice lab. That'll be fun. Okay, so plant versus animal really quick. Plant versus animal. What's going to happen if your cell gets a bunch of water in it like that? If it's an animal cell, then it could lyse. Burst. But plant cells don't burst. Plant cells have a cell wall, and it keeps them from bursting. They just get really fat, and the cell wall holds them together. They don't burst. but they get really fat. Okay, and then what happens the other way? It'll just shrivel up into like a little nothingness, right? It'll just shrivel up. So what happens to the animal cell is it just turns into like a little raisin looking thing, those clumps up. Sometimes it can make you have blood clotting. If it's your red blood cell that's doing that, it's bad. You don't want your red blood cells to change shape or size. That's bad. But if it's a plant cell, then what happens is the cell wall shrinks away I'm sorry, that was a lie. The cell membrane shrinks away from the cell wall, and the cell wall stays structurally there. Remember, the cell wall is very structureful. So it doesn't lose, the cell itself doesn't lose its structure, but the cell membrane shrinks and kind of collapses in. Okay, so that's the difference between plant and animal cells if you drop them into solutions, because plant cells have cell walls, which kind of change the way they behave. Okay, I hope that's very helpful. You need to study and make sure that you've got those terms down for the next quiz. Okay, have a great day. I'll see you soon.